I'm going to show you my own idea how to detect roundabouts using machine learning from car traces. The guys before me had a presentation about the presentation, and as you should probably know, the good presentations should start with the hype. So as the hype, I'm going to show you a small video. If you feel a little bit confused, yes, this is the presentation about roundabouts. But you must probably imagine how sophisticated task it would be to develop a program that would be able to flip pancakes, and how many different situations, real-time scenarios would have to be considered in order to make it possible to test it and implement it. And in this presentation I would like to show you that sometimes it is struggling to develop such a difficult program should have to be reconsidered, because instead you can program the machine to learn to perform this task by itself. And in this presentation I will tell you why it is only sometimes that you want to try using machine learning. Then I will tell you why the topic is about roundabouts. I will tell you our first approach with my previous team. Then, before I go to the main part of the presentation, when I show my approach, I will introduce a little bit neural networks to those of you that might not have the idea how they really work. So, why sometimes? Machine learning is absolutely and undoubtedly great, wonderful, amazing topic. And if you are at least a little bit enthusiastic, and if you haven't heard before about this, today you will fall in love. And when you come back home, you will start learning machine learning, and you will get this feeling that machine learning can solve all the problems in the world. And then finally, a beautiful day will come when you will write your first successful implementation of machine learning. And not only you will think that machine learning can solve all the problems in the world, you will say that every problem in the world should be solved using machine learning. But then, unfortunately, sad times will come, you will fail a little bit, and probably you will think you will never use machine learning again. But I really insist that you should try to continue using machine learning reasonably. Sometimes. Exactly when to use machine learning, I will conclude my presentation with my thoughts about it. And now I will tell you why the topic of roundabouts. So when I was working in my previous team with Magda in Mau, we had a problem. We were asked to check one of the algorithms. People riding cars can report, with our devices, can report that they see a roundabout in the place where, in fact, on our map there is no roundabout. And there was already an algorithm, a service, that could tell from other traces, that could assess if the roundabout is there or not. And the problem is that this algorithm was not working very nice for all the cases. In fact, for most of the cases it was not working. And we were asked why. So we looked into the solution, we looked into the code, we saw what we saw, and trying to be as politically correct as possible and as diplomatic as possible, we answered that many things were wrong. It is a bit funny now, but it is not the fault of the people who designed the algorithm, because they truly said it is just an algorithm, but other people higher than them decided that they are so excited that it needs to go into the production in form of the prototype. So please don't laugh. And in this algorithm, you could select the layer in Cartopia, and you could click on the roundabout, and when you click on the roundabout, or whatever, you can click whatever, and you have a bounding box in which you will have circles, and with the confidence level that there are roundabouts there. And as you can see, around the lotników primorskich was detected. But sometimes there was no roundabout, and in many cases, the strange scenarios happened that the roundabout was detected while it was not, but it was not the biggest problem. Because if you click a few pixels aside, then suddenly from the 45% confidence level, we magically have now 50% confidence level, while this is still the same roundabout. And if you master yourself in clicking properly, you would be able to make the roundabout disappear. Of course, detecting roundabouts, more difficult cases, was absolutely out of question for this algorithm. So, together with Hubert and Nelson, we decided to design our own algorithm for this and our own service. And as it is promised on the box designed by Janek, there is no regression. It also detects roundabouts primorskich, which you can see here. And what is absolutely unbelievable, it detects roundabouts primorskich with the same confidence when I click here, here, and even here. What is more, in very strange situations, it does not detect roundabout, mostly, and it also supports more complicated roundabouts. As you can see here, the multi-level roundabout was also detected. What was the approach about? First, we downloaded CPOS files. For these CPOS files are files with traces from cars that use our GPSs. And we constructed a Bezier image of traffic, so you can see it here. And then for this image, we were detecting holes morphologically, and for every hole, we made the transformation into polar form. So we unfold the picture into polar form, so that now you can see the top edge is the center of the roundabout, and the roundabout is along the picture. From such picture, it is very easy to detect the road along the roundabout, and this road can serve as a mask for traces. And now we only analyze traces on the roundabout, and the problem is linear, one-dimensional problem, where we can find the directionality easy and the exits. So the first thing that we can do with this is just preliminary find some candidates. If the directionality is unique, if there is not too much discontinuity of traces, we can say this is a candidate for roundabout, and then we can use some more sophisticated algorithm to find where are the entrance exits, find the distribution inside every entrance exit so that we know that every part of the roundabout has some traffic and we know it's in correct direction, then give some penalties and so on. And finally, we will be able to say with some confidence that the roundabout is there. And we are really proud of this solution because we thought it's really interesting. Well, in fact, it is interesting. And it gave quite nice results, especially in comparison to the previous algorithm. But we wanted to make it even better. So we looked into the false positives and false negatives, and we wanted to improve our precision. And sometimes we found a situation that there was some noise, and there were trucks going through the roundabout, and there were more than one hole for a single roundabout. So we decided to add a few ifs here and there, and it solved the problem. But then, after solving this problem, some other situations came up where we filtered out some places, and then roundabouts which were earlier detected stopped to be detected. But we were really lucky to find the proper solution. Adding a few special conditions, we were able to solve more and more situations. But solving these situations, it turns out that there were other cases where there was clearly no roundabout, but because of different noise tracks, we detected roundabouts. And for all of these cases, a solution came down from heaven. Let's add a special condition. And we were slowly dying in the labyrinth of special cases, and finally, a decision from the management came, the change of priorities. Roundabouts are no more important, there is no time. This was one of my first projects here after I finished my PhD at the Technical University, and I couldn't understand there is always time. So I decided to continue my project secretly during romantic nights at home after work, and I said to myself, it's enough. I'm not going to add any more spaghetti whenever I see another case. I want to say, when I see another case, I want to say, no, this is not a roundabout, my dear computer, please do not detect it again. And it is possible, thanks to machine learning. And before I'm going to introduce it to you, my approach, I will first introduce briefly how machine learning works as an example of neural networks. Sorry. So, in many problems, you would like to write an algorithm which is going to take some features and arrive at some conclusion. In machine learning, you are not going to write this algorithm. You are going to provide the machine with a mathematical model, and you are going to provide it with examples with known conclusions, and you want to make this mathematical model extrapolate from these examples to find the conclusion for an unknown case. Let's start with something really obvious. Let's say we want to predict the price of the car if we have its power. So we can say that our mathematical model is just linear regression. So we put some examples. The algorithm can extrapolate easily because it's linear regression. The more examples we have, the better linear line will fit. And what we are trying to do is obviously minimizing the entire cost of this, while a single cost is just an error between one example and how it will be predicted, or a square of it. It is easy to minimize, and if we minimize this function, we will find the best fit. So we will find a line with one parameter, and we are able to predict car price. But now, if we want to make classification, so we have a car weight, and we want to say if it's a passenger car or a truck. And now fitting linear line in this, maybe it's not the best thing, because we may have some extreme examples which really change this line. So we should better fit sigmoid, and this is called logistic regression. It is a little bit more difficult in terms of finding the minimum cost for the entire function, because especially if we have many features, this is a nonlinear problem. So the better way is to use gradient descent. This is an algorithm in which you have the cost, and you don't need to know it, but you just make a random try, and for this you only compute derivatives in every case, and you go down the hill. And when you arrive at the smallest cost, you know the parameters of the solution that are quite almost, maybe optimal, maybe almost optimal. Anyway, you are able to, after minimization, you are able to distinguish passenger cars from trucks by a single point, a single threshold. If you have two features, this will be a line. If you have three, this will be a plane. But anyway, what you still lack is the possibility to distinguish more complicated things. When the boundary distinguishing two different classes is not a straight line, it's not a simple plane. So, well, you may approach it in different ways. You may make combination of these features, multiplications, squares. This is a valid solution, but it has also some drawbacks. I'm not going to talk about this because there is a better solution. You must first realize that maybe why it is impossible in a simple way is because of the fact that you have very primitive features and quite high-level conclusion. So maybe the solution will be to add some intermediate features inside, which will be easier computed from the features that you have, and then from this, a bit more complicated features, you arrive at the conclusion. It can be proven, but it can also be easily imagined that two stages of simple decisions may arrive at a very complex decision, in fact. So we can do it, we can try to do it. Everything would be nice, but it seems that nightmare would be to train this, because now you have a lot of nodes inside and you have to train them all, because you have all these intermediate features which you have to teach to the to be able to detect properly. Because, mathematically speaking, we want to minimize the entire cost. And in order to minimize entire cost, we can use gradient descent, but we need derivatives. And we can only find the derivatives if we know the errors at every stage of the process. So we have to train it. No, we don't have to train it. We have a perfect algorithm to omit this training, because what we can do, we can initialize the system randomly, and we can put our examples inside the system, and we will go through the system absolutely random. It will detect something. There will be a lot of wrong things, but we will have an error in the end, which, after we revert this network, we are able to backpropagate again through this network, and we will find these errors at every stage, at every node. If we have these errors, we are able to compute derivatives, and we have the derivatives, we are able to compute gradient descent. So we are able to minimize this without training any node. And what is even more amazing is the fact that we don't even need to think about these features, because the algorithm, thanks to the fact that we initialize it randomly, and the algorithm itself backpropagates the error, it doesn't care what features we were thinking in the beginning. He will form them, he will modify them in such a way that to best arrive at the given conclusion. So even if we thought about some feature, it will be totally different after the algorithm uses it for its own purpose. And if we don't need to care about any of these features, algorithm will do it the same. It's the only thing to choose the number. So we can choose much more features if it's so easy for the algorithm, and we can use it to classify really complicated things in such a way. And even though it is far away from what our complicated mind does, the principle is very simple. We also have a neural network in our head. The difference is it is not artificial. So, after being so excited, I am forced to tell you that this is idea of 40 years old. And it is in every book, it is in every library of every language. You can easily implement it. And in fact, today, in order to use this artificial brain, you do not need your own. You just take the book, you just define some parameters, and you have your network ready to classify anything you want. Everything is in the book. Or not. So let's come back to our example. We can easily define a nice neural network to solve any problem. It can imagine wonderful things. We know it can because we just read a book. And we also have our set of examples, our traces, a lot of them, ready to help us to detect our roundabouts. But the question is how we are going to put these traces into our neural network. We just said that we need to define the network. We have a specific, well-defined number of input features, and there are very many traces. They may be long, they may be short. How to make it, how to put it inside the network. So maybe the first idea is to use the features similarly to what we did before. The average directionality, some penalties, and so on. Maybe let's use this for the feature. And it would work, it maybe detect some roundabouts. But the problem is that even though you use this neural network, you have to put a lot of your own algorithmic power to compute the features. And what is even more important, by computing the features yourself, you deprive the neural network of the knowledge what was the raw data, and it will not be able to think, to learn anything else that you already put into these features. So it will be a little bit handicapped. It will be biased by your unawareness of possible problems that you did not capture with these features. So maybe a better idea would be to just use the image of traffic and put every pixel as an input feature to this network. And it would work. It would detect a lot of roundabouts, but there will be a lot of false positives, a lot of wrong detections, because what you fail to provide with such a picture is the directionality of traces. You fail to provide the information how every single entrance is approached by the car, how it is exited. You lost all this beauty in this blurred totalitarian picture. So, defining input to the network is probably the most challenging task in machine learning, because the machine learning algorithms already exist and you can just download them. But when you have to form input to this network, you will have to stop using the book and start using your brain. And now I'm going to tell you how I managed to solve this problem. It's quite an original idea, I hope. So I hope you will enjoy. So I download the traces from CPOS files. I put them on the grid. The grid is of 10 by 10 meters. And I iterate through this grid. And for every cell, I consider only those traces which pass through this cell. And what's more, I consider only those parts of the traces which, from the perspective of this cell, are in the future. And finally, I limit my consideration to another bounding box of, in this example, 40 by 40 meters, and then I squeeze this 40 by 40 meters bounding box into the original cell of 10 by 10 meters, and what is the result is a mosaic-like picture of the roundabout, which you can see here. So if you look at it, you can still see the overall traffic characteristic. You can see this circle, you can probably say it's a roundabout. But what else you preserve in this picture is the sequentiality of individual traces. If you look at the first cell that I selected for you, you can see that some of the cars were going around the roundabout, some of them exited the roundabout. What is what else you can clearly see is the preserved speed information, because, for example, here you can see that the points are really dense, one close to another, which means that the cars in this part were going very slowly, because you have dense points. Here, for example, you can see that from the center you have a lot of free space, which means that the cars were going really fast. So if you look at this picture now with this knowledge, you can easily distinguish the entrances to the roundabout where the car was slowing down and the exits where they were speeding up. So this kind of picture preserves almost all the information that we probably need, and it is so close to the raw data, and we cannot capture almost everything that is in raw data. And after a little bit of removing of what is not important, I arrive at a consistent network input of 6,156 features, each being 1 pixel of such an image, and I put it to the network, and I hope it can understand everything. Having this kind of input, I'm ready to start generating, teaching the network to understand. Thanks to Anya, I got the locations of all the roundabouts whenever I needed that are in our map, marked as roundabouts. And for all of them, I downloaded CPOS files. And I also wrote a MATLAB script to click through all of the roundabouts by myself and confirm that they are really roundabouts, looking at the traces. So the ground truth, I collected about 400 roundabouts, but I also collected about 2,000 non-roundabout cases of various types. I tried to cover as many possible examples as I thought. And from this set, I chose 80% to be my training set, and I also rotated these training set copies for a variety number of times, so that my network will learn that it doesn't matter what is the rotation, it always detects roundabout whatever the angle. And with this set, I was able to create a solution whose accuracy is over 96%. After the mind-blowing presentation of BIGOS, you would probably like to ask what the other measurements are, precision, recall, and so on. And to be honest, this is quite a symmetric problem. So this is the precision and the recall would be in the same level. Anyway, at this stage, I was happy with the results, and I was satisfied. My ambition was no longer killing me, so I decided to stop my secret project. But if I continued, what I would do next, just one step, one more thing. From the diagnostic curves, so if you look at the learning curve, you still see the potential of this algorithm. You still know that there is some variance, so maybe you could increase the number of training set, or you could decrease the complexity of the network and the results would be even better. So the potential is still there, that's why I was satisfied. The only thing I would need is time. And now coming back, what I would plan to do next was online learning. So I will tell a few words how I would do it. So I have my algorithm, I teach it with my training set, and then I'm able to detect, to process all the work, and gradually, of course, detect some errors on the map and send them to operations. And the operations could either correct this case, if it's really something that I detected was right, or do not correct. But this information could be fed back as another training example and put back to the machine learning algorithm. It will not be as easy as you think, because the batch learning is very optimized. If you have a lot of examples, you do it in a matrix way and you arrive quickly at the solution. But if you just give one by one examples, it might be more difficult. And for this, I would use stochastic gradient descent, in which a single iteration, a single arrow here, would be not computed by all of the examples, but just the one that arrived. What we would have with this is sometimes the gradient descent would go in the wrong way, but statistically it will arrive also near to the optimum. Of course it would take time, but I hope we would have a lot of examples because the operations are working. So, that's it. Let's come to the conclusion. If machine learning is so wonderful, so why use anything else? First of all, machine learning needs training, and training may be really expensive because collecting ground truth is expensive. If I didn't know Błażej from MOMA team and my task would be to detect signs, I would never use machine learning because I would have to take a picture of about 1 million signs probably, which would be very expensive. I would not use machine learning if there already exists a standard algorithm to solve a problem. However, I will use machine learning if the problem is complicated, non-intuitive, and it is very hard to find a proper algorithm quickly, and I quickly need the solution. Especially if there are very many special cases, which you saw in my case. I will certainly use machine learning if I only care about the final statistics. I want to have the good numbers, but I don't care what's going on in the twisted mind of the machine that I created myself. And I will surely use machine learning to show off, because machine learning is cool. So this almost brings me to the conclusion, and every good presentation should end with a hype also. As a hype, for the end, I want to show you the guy who trained a probabilistic neural network, a variation of a normal neural network, and this network was detecting handwritten digits. And then he selected one of the label and ran the algorithm backwards. So let's see what happened. So what you could see is that depending on the teacher, the neural network can learn its own perspective of the problem. In this case, it crystallizes its own handwriting skills. It has its own imagination. And please be careful when you let your network to imagine too much, and especially don't let it imagine our raw network, and particularly roundabouts, because when you do it, the results might be scary. Thank you very much.